Now, the last one that we have into consideration, which is the most prominent measure of central tendency that we take into consideration, is the standard deviation, or elaborately we call it as a root mean square deviation. If we calculate it as the square root of mean of the squared deviations from the actual mean. That is, you take how you calculate the standard deviation is, you calculate the arithmetic mean, you take the deviations from the arithmetic mean, not absolute values. With the sign you take the deviations, you square it up, sum of the squared values, divide it by the number of observations, and find the square root of it. Okay, so in the case of an individual series, we consider the standard deviation as square root of sigma over dx squared by n, where the dx value is x minus x bar, where x bar is the actual mean of your data set, and the coefficient of standard deviation is calculated as the standard deviation divided by x bar, where x bar stands for the mean. When you are using an assumed mean, that is, you are taking the deviation about an assumed mean, then your standard deviation is calculated as sum of all dx squared by n minus sigma of dx by n, the whole square. Okay, and when it comes down to the discrete series, it will be sigma over f into dx squared by n when the deviation is taken, or the dx value is taken as x minus x bar, where x bar is the actual mean, and sigma over f into dx squared by n minus sigma f of dx by n the whole squared, where the deviation is taken from an assumed mean. In the case of continuous series, it is the same, except that the deviation is taken from m, which is the midpoint of the class interval under consideration. The case of standard deviations, you have the x values, you calculate the mean value, take the deviation from the mean value, square it up, sum it up, and substitute the values in the equation as square root of sigma dx square by n, which gives you a standard deviation of 60.49, and the coefficient of standard deviation as the standard deviation divided by x bar, that is 60.49 by 100. And standard deviation in the case of discrete series is, again, you have the x values, you have the f values, you calculate, you take a as an assumed mean as 16, you calculate the dx values, you find the f into dx, you find the f into dx squared, and substitute those values in the equation for standard deviation to get a value of 3.21. And in the case of continuous series, again, the process is continued with the simple difference that here, instead of x, you make use of the midpoints, which may sometimes be denoted as an m, as the midpoint of the class intervals under consideration. And here again, there's one difference that I have used here. I've used a dx dash along with the dx, where I have divided my deviations with a common factor of 10. Okay, so we find that when you are calculating the standard deviation here, we are multiplying our standard deviation by the I, or the scaling factor with which we have divided the dx values to get the dx dash, which gives you a clear evidence that the standard deviation, though it is not affected by the change in origin, which is reflected by not adding back the a value, it is affected by the change in the scale. That is why we are multiplying back the 10 with which we had divided the deviations in our previous step. Now, when you want to find the combined standard deviations, you want two different data sets to be combined together, we go for a combined standard deviation formula. A simple one with 3 data sets is given to you here. You find the combined mean, and you use the combined mean to find the deviations from each of it. That is, d1 is calculated as x bar minus x1, d2 is calculated as x bar minus x2, and d3 is calculated as x bar minus x3, where x bar stands for the combined mean of set A, set B, and set C of the series that is given to you in this example. and substitute it to the equation for combined mean, which is given by n1 sigma 1 squared plus n2 sigma 2 squared plus n3 sigma 3 squared plus n1 d1 squared plus n2 d2 squared plus n3 d3 squared by n1 plus n2 plus n3 and the square root of that quotient value. Okay. Now, coming down, we have looked into the mean deviations, quartile deviations, and standard deviations. When you find a relation, an empirical relation that exists between the mean deviation, standard deviation, and quartile deviation, we find that the mean deviation is calculated as the 4/5 of the standard deviation, and the standard deviation comes in as the 3/2 of a quartile deviation. So, whenever two of them are given, the third one can be calculated, or whenever even one is given, the other two can be calculated using the empirical relation, which is clearly evident from the example that is worked out here. Now, again, we have the coefficient of variation or the coefficient of variability that is taken into consideration when you want to compare the set of variations that are there in two different data sets. Okay. So here we have an example where the table gives the age distribution of boys and girls in a high school. We want to know which of the two age groups have higher variability in the age. So we go in for calculating the coefficient of variation for boys and the coefficient of variation for girls, and we get that coefficient of variation for boys is 7.86, whereas coefficient of variation for girls is 7.34, which gives us a clear evidence that for the girls, the age among the girls in the high school is less variable when compared to the variance against the when compared to the age of the boys, or the among the two groups the variance is more or variability is more with respect to the boys. The properties, certain properties of standard deviation that are to be taken into consideration. We have seen in an example that standard deviation is independent of change in origin and it is not independent of scale. So sum of squares, when taken from the arithmetic mean, you may use an assumed mean even, but still when they are taken about the arithmetic mean, that gives the minimum sum of squares. And also x bar plus quartile deviation covers 50% of your data, whereas x bar plus or minus the mean deviation covers 57.51 of your data, and henceforth with the standard deviations as well. And when you wrap up the entire thing, we have looked into range, quartile deviations, mean deviations, and standard deviations. We find that range cannot be considered as a stable measure. It has many drawbacks, such as the fluctuations of sampling. It does not depend on every point under consideration, but it is used for a quick overlook into how your data is distributed. Quartile deviations do not take into account all the terms, though it is not affected by the extreme end values. And mean deviations are not capable of further algebraic treatment. If the extreme values are big, it will distort the result, because the mean and the median is taken into consideration. Plus it ignores the positive and the negative signs, that is, it ignores the values of the deviations. Whereas when it comes down to the standard deviation, it is considered as the best measure of dispersion despite the extreme term influences, but it is capable of further algebraic treatment, and it is not affected by the fluctuations of sampling. It is rigidly defined as well as it is stable. So among the four, depending on what is our requirement, we may choose any of those. If you simply want to know what is the range of your values, you can go for the first one. If you want to find a dispersion value, that can be used at a later point of time, maybe for testing some series, or maybe for a prediction value or prediction of a value. In such cases, we may go for a standard deviation. So it is purely depending on what kind of data you are analyzing and what further requirement that you need from the measure of dispersion. You choose any of these measures of dispersions for your calculation. Thank you.